All right, second part of estimates and sample sizes. Let's talk now about estimating a population mean. Last time we talked about estimating a population proportion. Now we're going to estimate population means, and the steps are going to be really similar. So, estimating a population mean. If we're trying to estimate a population mean without knowing the population standard deviation, normal distributions have too much unreliability for small sample sizes. So before, for normal distributions where we knew the standard deviation sigma, we were finding the critical values, z-scores, by using x bar minus the mean over the standard deviation. But we can't use this now because we won't know the standard deviation. So now we're going to use a different critical value called the t-value, the student t-value. It's a really similar formula. It's the sample mean subtracted by the population mean divided by the sample standard deviation, s, over the square root of n. This is much more common. We usually don't know the population's standard deviation, but we usually can figure out the sample's standard deviation, that s value. Okay. This is called the student t distribution. So just like when we had the standard normal distribution chart and we looked up all of our z-scores, the critical t values, the student t values, there's a similar chart. I'll talk about the area in one tail and area in two tails and degrees of freedom in a minute, but I want to bring your attention to the bottom. This is much shorter. This is a much shorter chart, and I only have our chart going up to degrees of freedom of 40 on this screen. After 40, the charts tend to jump for degrees of freedom 40 to 60 to 80, and some of them don't even include that. So if that frustrates you, there will be ways of estimating, but you can also use your TI-84 to calculate these t values, just like you used maybe the TI-84 to calculate your z values. Okay, a comment on area in one tail versus area in two tails. We're primarily going to be concerned with the area in one tail in this section, but the difference is, area in two tails in this section, but the difference is whether you're considering both the high end and the low end or just one side. So there's a picture of one-tailed test versus two-tailed tests on the right. In this chapter, don't worry too much about that. We'll get to that later. Okay, so let's talk about degrees of freedom, because that was a big part of our chart back there. Given a sample size n, for simplicity's sake, we're going to calculate what we call the degrees of freedom as n minus 1. So for example, if we take a random sample of 12 Guinnesses from the factory to test the mean output amount of alcohol in a beer, and we need to calculate the degrees of freedom for this sample, if there are 12 in our sample, 12 minus 1 gives a result of 11 degrees of freedom. And 11 is the number we would use for our chart. Okay, another example. Let's say a sample size of n equals 7 is a simple random sample selected from a normally distributed population. Find the critical value t sub alpha over 2 corresponding to a 95% confidence level. So we did a lot with confidence levels and z values on the last video. In this one, notice we don't know the standard deviation for this. So here's what we're going to do. First, we're going to find the degrees of freedom. The degrees of freedom is n minus 1 or 7 minus 1. So degrees of freedom is 6. And t of alpha over 2. So if we have a 95% confidence level, alpha is 5% or 0.05, which means t sub alpha over 2 is t sub 0.025. Okay, so going to our chart here, there is the degrees of freedom for 6. Here's the column for area in one tail, 0.025. And it looks like we get a t-value of 2.447. Okay. So our t-value for this would be 2.447. Okay. Margin of error. If you remember the last video, we spent a lot of time finding the margin of error for our confidence intervals for the z-scores. For the t-values, the margin of error is really similar. The margin of error is the t-value times the sample standard deviation divided by the square root of n. So let's do a quick example. Assume you're collecting a random sample of 49 subjects to measure the effects of a cholesterol lowering drug. You find that this sample lowered their mean cholesterol by 0.4 points, and it had a standard deviation of 21.0. Calculate the margin of error for a 99% confidence interval. Okay, first, we don't know the standard deviation of the entire population. We just know the standard deviation of the sample. So we're going to use the t distribution, not the z's. So that means we need to find degrees of freedom right away. So 49 minus 1 gives us 48 degrees of freedom. Then we need to find our critical value, the t value. So let's see, for a 99% confidence interval, this would be t sub, oops, go back, alpha over 2.005 if we do 1% divided by 2. Okay, degrees of freedom is 48. So, 48 is not on this chart. It only goes up to 40. And we had a 0.005 area in one tail. So that's our first column. So here's what we're going to do. You can either use your calculator or, and I'll post a video on how to do that in this section, or we can estimate. So I want you to notice that as our t-values, as our degrees of freedom rather, get bigger and bigger and bigger, those t-values get really close together. So we have, like, for 38, 39, and 40 degrees of freedom in the first column, we have t-values 2.712 and 2.708 and 2.704. They're not very far away from each other. So 2.70, or actually rather 2.678, which I cheated and used my calculator, but it's really close to 2.70, which would be fine. We're going to estimate what we think our t-value is. If you're using the chart, you're going to have to do that kind of estimating. 2.7, by the way, would be perfectly okay. If you're using a calculator, it should give you a result like 2.678. Okay, got the degrees of freedom. We've got our critical value. Let's find our margin of error. So we're going to use the formula from the top of the page, the t-value times the sample standard deviation divided by the square root of the number of subjects. And when we do that, we get a margin of error of 8.034. Okay, so let's find our confidence interval. Just like in the last section, we're going to construct the confidence interval by taking our mean and adding adding the margin of error and then subtracting the margin of error. So back to our example with our degrees of freedom 48, our t-value 2.678, and our error of 8.034, our mean was 0.4. So 0.4 plus the margin of error, 8.034, and 0.4 minus the margin of error. So this means that our population mean, or mu, is somewhere between negative 7.634 and positive 8.434. So there's our confidence interval. Okay, the math works out great. Let's interpret this a little bit. What does this mean? So one thing to notice is this was supposed to be measuring the effects of cholesterol lowering drug. So this mu is the mean number of points that this drug lowered cholesterol. 0 is in that interval. Since 0 is in that interval, then it's quite possible that the drug did not lower anybody's cholesterol at all, lowered it 0 points. So since 0 is in our interval, it is possible that the drug does not work. Just something to point out about interpreting our results. Okay, steps for calculating a confidence interval if you don't know the population standard deviation. First, find the degrees of freedom. Then find your critical value, that t-value, using your t-distribution table or using your calculator. Then find the margin of error. This is the formula that we're going to use, t times the sample standard deviation divided by the square root of the number in the sample. And then lastly, when we construct the confidence interval, we take the sample mean and we add the margin of error, and then we subtract the margin of error. Okay, one more quick example. In a study to test the efficacy of using magnets to treat back pain, 40 patients were given a treatment with magnets and also a sham treatment without magnets. Pain was measured on a scale from 0 to 100. After being given the magnets treatment, the 40 patients had pain scores with a mean of 11 and a standard deviation of 2.5. After being given the sham, or say placebo, the 40 patients had pain scores with a mean of 10.6 and a standard deviation of 2.1. Let's construct a 90% confidence interval for both of them. So for the mean pain scores for the patients using the magnet treatment, and the same for those using the sham or the placebo. And then we'll compare the results. Does it appear that the magnet treatment is effective? And I misspelled effective. Degrees of freedom, for starters, for the first one using the magnet treatment. 40 minus 1 is 39. The t-value corresponding to a 90% confidence interval, if we look it up on our chart, should get 1.685. Plugging the t-value and the n, which is 40, into our margin of error, combined with a standard deviation of 2.5, we should have a margin of error for the patients with the magnet treatment of 0.666. So adding the 0.666 to their mean and subtracting it, we get a confidence interval of 10.334 to 11.666. Okay. Same thing for the patients that had the sham treatment. They had the same degrees of freedom. They have the same critical t-value. Their error is different. Margin of error is different because their standard deviation was 2.1 instead of 2.5. So their margin of error is 0.559. And then we're going to take that and add it and subtract it from the mean, which was 10.6. So when we do that, we get that their mean is between 10.41 and 11.159. But since these confidence intervals